So, good afternoon and welcome to our seminar. So, as you know, this is the last seminar before summer holidays. And the topic for today is about energy flexibility. So the speaker is Rui Lopes, so a member of our center. And for the discussion period, we'll have the help of Bruno Guerreiro. So thank you all for attending this session. And Rui, the floor is yours.
Thank you, Professor. Hi, everyone. Thank you for joining this last seminar. I hope you are seeing my screen now. Yep, thank you. Well, this seminar is about unlocking energy flexibility to support energy transition, a topic that seems to be at the news during the last days. So I will address the importance of energy transition given the current context, and also the challenges that might be imposed to existing distribution grid, which can be related with this energy transition, namely the increasing integration of renewable energy resources and the increasing electrification of energy demand might impact the operation of distribution grids. And therefore, what we have been studying is that energy flexibility can contribute to minimize the possible negative impacts on energy grids, namely the power grids. Then I will speak about energy flexibility characterization methodologies and how these methodologies can be used to achieve certain objectives like optimization of PV self-consumption, reduction of electricity costs, or even reduction of CO2 equivalent emissions associated to a specific load profile. And I will finish this presentation by presenting some ongoing projects where our group is working on at the moment, which are related with this topic of energy flexibility. So I will start by showing you this plot, which gives us the CO2 equivalent emissions related with the energy sector. And as you can see, there is steadily increasing since 1950. And there are some events that seems to have an impact on this increasing. For instance, the second oil shock, the financial crisis of 2008, or of course, the COVID-19 pandemic of last year. You can see here a very important decrease in CO2 equivalent emissions. And as the energy sector accounts for around 3/4 of CO2 emissions, you can see that rate of change of global primary energy demand also suffers with those events. You have here the same second oil shock, the financial crisis of 2008, and again, the COVID-19 pandemic in 2020, reducing total primary energy demand at global level by more than 5%. So it seems that this increasing in CO2 equivalent emissions in our atmosphere is also related with increasing of our global average temperature above sea level. You can see here the temperature anomaly from 1880 until last year, and you can see that the temperature deviation relative to 1951-90 1980 average is already in 1 degree. This temperature anomaly is having several impacts on different aspects of the operation of our planet. One of those is the sea height variation. And this plot here shows the amount of increasing it has been registered since 1993. And you can see that it's already in 100 millimeters in average. And I would like to highlight this anomaly because this is very important for a country like Portugal with our large seacoast. So other examples of impacts exist, like the warming ocean and also the increase in water level. It's related with warming ocean. The shrinking ice sheets and so on, also decreased snow cover. So, and also the frequency of extreme weather events seems to be increasing, which might be related with this climate change. For instance, Canada has registered more than 50 degrees this month, when on average for that period, they should have around 20 degrees. So Siberia, another example, is achieving 35 degrees, which is much higher than their normal temperature. So it seems that climate change is real, and it is the motivation for this energy transition that is taking place. And acknowledging that this energy transition is needed, several countries in the world, including Portugal, have signed the Paris Agreement, where they established the goal of limiting global warming to 2 degrees only, while making the best efforts to limit to 1.5 degrees. This was before the IPCC, International Panel for Climate Change, published its report suggesting that a huge difference will occur in terms of climate change impact if we restrict this global warming to 2 degrees instead of 1.5. So the difference is high. And therefore, they made several scenarios, and they published in this report, where they show us that it is possible to restrict global warming to 1.5 degrees Celsius. So here in this image, we have several paths of global CO2 equivalent emissions, but let's say most of them are scenarios where global emissions achieve a net zero scenario by 2050. And therefore, taking this into consideration, the International Energy Agency has also developed a specific scenario for the energy sector. And here starts the important material for our research, where they show a specific scenario in order to achieve net zero emissions by 2050. And this is great. It shows that it is possible. Not all technology is available at the moment. Some is in the demonstration phase or prototype phase. But for instance, between today and 2030, all the technology is already available. So this decrease in CO2 equivalent emissions is driven by several factors, including increasing energy efficiency. And here we can see this. Global energy demand compared to 2020 will decrease by 88% in 2050. taking into consideration that economy will double in size during the same period, and that we will have 2 billion people, more 2 billion people living in our planet. So energy demand will increase. If energy demand would increase if current energy intensity was maintained. But what this scenario shows is that it is possible to, despite the economy grow and populations increase by 2 billion, it is possible to reduce energy consumption. Then an important contribution is the decreasing dependency from fossil fuels. It decreases from around 4/5 today in 2020 to around 1/5 by 2050. Most of the remaining energy supply will come from renewables. So the third factor is the integration of renewable energy resources. And to contribute for both the integration of renewable energy resources and increasing energy efficiency, some fuel switching will occur. We will have more electrical vehicles instead of fossil fuel-based vehicles, and other changes related to the electrification of energy demand will take place. For instance, instead of gas boilers, we will have more heat pumps and so on. So increasing electrification of energy demand is also an important factor. In terms of technology value, as I was referring, between today and 2030, technology is already available in the market. What we have to do is to increase solar and wind contribution by 4 times. It's possible, that's already good. It's not easy. It depends on policymakers as well. And also the integration of electrical vehicles. It has to increase by 18%. At the same time, energy efficiency has to increase in order to reduce energy intensity by 4% a year on average. The problem, which is also an opportunity for us research institutions, is that from 2030 to 2050, some technology responsible for further CO2 reductions is not yet available. It is at the demonstration or prototype phases. These include batteries, hydrogen electrolyzers, and direct air capture and storage of carbon. Those are the main fields that still need more research, and therefore they represent an opportunity. It seems problematic, but if we think that we still have around 30 years, it seems more feasible, let's say. So far, the pace has been impressive. It's not enough. We have to increase solar and wind by 400%. Here we have the historic integration of solar photovoltaics with more than 500 gigawatt at the moment. Well, this data refers to 2019. I could not find yet 2020, but it's already quite good. It should increase even more. Portugal has already more than 1.3 gigawatts and will increase to almost 10 gigawatts in 2030, which is quite an evolution. In terms of electrical vehicles, the growth so far is also exponential. You can see here with data already for 2020. China and Europe and the United States are of course leading, with China presenting this exponential growth as well. And we have more, in terms of market, we have more passenger light duty vehicles or light commercial vehicles, as it is demonstrated in this image. So in this analysis of the International Energy Agency, where they show that it's possible to achieve net zero energy emissions by 2050, they also cluster the contribution, the total global contribution by sectors. And they cluster in three main sectors: industry, transport, and buildings. And I would like to highlight that building sector plays a huge role on this energy transition, not only in terms of energy transition per se, but also the social aspect of it, reducing, for instance, energy poverty. So floor area in buildings worldwide is expected to increase by 75% between today and 2050, 75%. And we should take into consideration that at the moment, buildings are responsible for around 40% of the final energy consumption in Europe, and around 36% of CO2 emissions in our continent. So to achieve the net zero scenario by 2050, we should increase energy efficiency in buildings and increase electrification of energy demand. Those are the key messages. These refer us to the concept of nearly zero energy building, and more and more of those buildings will be found in our countries, in our country, in Europe, and in other places of the world. It should be referred as well that more than 35% of European building stock is more than 50 years old. So the rate of renovation is expected to be between 0.4 and 1% per year between 2020 and 2050. So the opportunity to deploy the required technology is there, and we should make advantage of it. And for you to have an idea, this 75% of increasing between today and 2050 is the same as increasing the building area by the size of the city of Paris per week. So quite impressive. Here we have an example of a nearly zero energy building located in Norway, in Trondheim. This is in fact a living lab where researchers live here for some months. And the interesting feature of this building is that it is carbon neutral in terms of the entire lifetime. So during the collection and installation of materials, there is an energy demand without offsetting the respective carbon emissions. During construction, the same applies. But then during usage phase, there is generation of through a photovoltaic system, as you can see here, that will compensate more than the CO2 emissions associated to the usage phase. And then at the end of life, we have also, they have also some recycling, which offsets some carbon emissions. I believe Daniel Aline, our colleague, show you another example of nearly zero energy building located in Portugal, Solar 21. That building achieves near net zero energy status by a year period. This one is a bit different. It offsets the entire emissions of CO2 during its entire lifetime. So several definitions exist. The important part is increase energy efficiency and the integration of renewable energy resources. Normally, giving the nature of such buildings, the photovoltaic systems are chosen to supply part of the required energy. So this was what I had to say about energy transition in terms of what we can expect: increasing electrification, increasing energy efficiency. What I will show you now is an example that we should take into consideration when analyzing energy transition, because some changes will occur in the operation of our distribution grids. And this example shows that, okay, this integration of renewables is good, but we should, of course, take into consideration that some negative impacts might occur given the nature of, for instance, reverse power flows. But it's not a bad thing. It's just to show that, okay, we have to be aware of this and make and develop the solutions that will mitigate possible negative impacts. And these solutions can, for instance, use the available energy flexibility to control a set of storage devices, for instance. So, and as an example of these impacts on the operation of distribution grids, I will show you a case study that we conducted taking into consideration a neighborhood composed by 19 buildings located in Évora, Portugal. These buildings do not produce energy on site, so we, to study the increasing integration of renewable energy resources, in this case photovoltaic systems, we converted these buildings to nearly zero energy building. Of course, this was on a simulation environment, but the load diagrams and other information is real. Only the simulation part is, of course, on a simulation environment to provide us with these scenarios. So we studied 20 scenarios. The first one is the original scenario where none of these buildings produce energy on site. And then we have 19 additional scenarios where at each additional scenario, one building is converted to nearly zero energy building by producing as much energy as it consumes at an annual basis. So basically, assuming that photovoltaic systems will be installed, we design photovoltaic systems in order to offset the entire energy consumption for 1 year. Here is the load diagram for the original scenario. You can take into consideration the 19 buildings. You can see that during winter, electricity demand achieves higher peak values. This is related with the comfort needs of the users, where they use electrical heaters. But in the summer, we do not have an increase, given that we were expecting that would be associated to air conditioning. And this is because they do not have air conditioners. And you can, as you know, Évora can get the temperature in Évora can get very high, and this is a signal that these users are probably out of the comfort zone during the summer, and it might give us an idea of energy poverty as well. In fact, our colleague João Pedro Gouveia has carried out several studies on this. You are referred to these studies to know more about this topic. Here, it was not our concern. We were concerned about assessing the impacts of increasing photovoltaic generation in this grid. To assess the impacts, we assess the increasing aging introduced by these scenarios on the distribution transformer that connects medium to low voltage grids. So for the here we have the average daily load diagram at the output of the transformer. And this first curve here in black represents the scenario with no photovoltaics generation. Then the other curves represent different scenarios. For instance, this one here represents a scenario where 4 buildings were converted to nearly zero energy buildings by producing as much as they consumed over a year. And you can see that the average load profile decreases around noon, given the solar resource availability, and that when we start to increase the number of nearly zero energy buildings, we start to have more and more reverse power flows with higher magnitude. Such magnitude achieves values higher than the original peak demand at evening. And this is the part that might introduce negative impacts on losses, protective devices, and distribution transformers, for instance. Here, we study the impact on the distribution transformer. This is not bad, it's just we need to be aware of this. So solutions using the available energy flexibility would have to be implemented, or we simply would curtail this energy generation. But of course, that means we would have losses. So this is an example where we could transfer some energy consumption from these parts of the day, evening and morning, to periods around noon, when the coincident solar generation of these 19 buildings is higher. We could use batteries, thermal storage devices, like heat pumps, or air conditioning as well. We could cool the building during the morning or during noon to avoid cooling at evening, and so on. Several examples exist. In terms of results, we have here the maximum load at the transformer output for most of the scenarios, while the generation is not so high. This yearly peak load is around 1.5 times the nominal load of the transformer, which is according to normal operation. But as we continue to increase the number of nearly zero energy buildings, we start to have negative values for these peak loads, meaning that a reverse power flow is registered, and those values in absolute value, let's say, are higher than the previous demand peaks. Also, the oil temperature, the hottest spot, increases from 139 degrees to 190. This would mean that the transformer would probably fail, or at least would have huge thermal stress. Then the aging of the transformer would increase from 8 days to more than 2,000 days. So the transformer would operate, but the aging would be very accelerated. In terms of daily peak loads, I can present you here a plot where you can see the peak loads in 2 different scenarios, with zero energy buildings, which are the gray marks, and the scenario, the other extreme scenario, where all buildings are converted to nearly zero energy buildings, the black marks. You can see that for the original scenario, peak loads are registered mainly during evening, as I referred previously, and that when we have the 19 buildings converted to nearly zero energy building, most of the peak loads occur during noon, and that these peak loads in magnitude are higher, in absolute value, sorry, are higher than the ones registered during evening. And what we also observe is that when the solar resource is not available, that we have the the scenario with all buildings converted to nearly zero energy building having the same peaks at evening. So in this case, transformer is supporting the, let's say, peaks both during noon and evening period. So what is the role of energy flexibility? Well, as I explained you before, we will observe increasing integration of energy conversion systems based on renewable energy resources. We will observe increasing electrification of energy demand, where the conversion from fossil fuel cars to electrical vehicles is an example. And at the same time, we have to increase the resilience of our grids, because during these extreme weather events, our grids are under higher stress, while we also aim to achieve CO2 reduction. This CO2 reduction I'm referring is the one associated with electricity production. So the CO2 content per unit of produced energy varies throughout the day. So we should be flexible also to decrease consumption when CO2 is higher and increase when CO2 is lower. But this, of course, is the best scenario. So given these changes, flexibility can be found on both the supply and the demand side of power systems. Our group is conducting the research focused on the demand side flexibility. And here we have an analysis of a plot from the International Energy Agency that conducted an analysis on flexibility needs in 4 different regions of the world. And these flexibility needs, of course, increase by the size of the country. But if we see in terms of share of peak demand, we see that India, in the next 10 years, will need flexibility in around 15% of the yearly peak demand, which is huge. This can be offered, as I told you, from the supply side, but also from the demand side. The demand side is yet to be exploited. There is some work already, but much is still to be done. So our focus is mainly on the demand side. And here, the building sector plays a huge role, as I told you before, because we have the opportunity, given the renovation pace we are going to observe, with around between 0.4 to 1% of renovation per year, and also the increasing of 75% on the building area we are going to observe until 2050. We have here a huge opportunity to deploy technology in order to use the available energy flexibility. And taking this into consideration, in 2014, João Martins, Daniela Linné, and me, we joined the Annex 67 Energy Flexible Buildings from the International Energy Agency. This project had 36 entities from 16 different nationalities, where the concept of energy flexibility started to be more and more developed. And the output in terms of definition was that energy flexibility refers to a building's ability to change its demand or generation according to local climate conditions, user needs, and grid requirements. This definition collects the 3 main contributions in terms, the 3 main factors, let's say, when characterizing and using energy flexibility, which are climate conditions, user needs. So we cannot change energy demand without taking into consideration the comfort needs of the users, and also the grid requirements to which we should interact in order to change energy demand. In this annex, in this project, we developed a methodology which is a data-driven methodology, to characterize the energy flexibility in buildings. So this methodology can be used without specific information of the system providing flexibility, a building or a cluster of buildings, or a standalone system like a water pumping system, but it uses only the data associated to the energy demand and a so-called penalty. So we assume that a building is smart enough to react to a certain penalty in order to minimize the cumulative penalty over a specific period of time, for instance, a day. What can be seen as a penalty? The price. The price of electricity that changes throughout the day can be seen as a penalty. So a smart building, or is a building in our study that is able to react to a change in this penalty in order to decrease the cumulative penalty. Here, cyber physical systems are instrumental, since sensors, controllers, supervision systems, and communication with grids and other operators is required. And we observed also that different buildings have different responses. These responses, we call this flexibility functions. So flexibility function, and for our colleagues from control, from the control area, you can see that it is basically a step response of our building energy consumption. So what we did was to characterize the energy flexibility in terms of the response of this building when a change in the penalty is registered. Here you can see an increase. You can think about this penalty as a price, an increasing price. When this increasing is registered, the smart building reacts, decreases energy consumption until a moment that it cannot sustain this reduction anymore and starts to increase energy consumption again with a specific rebound. We have several characteristics to describe this flexibility function, like this area A, which is the amount of energy we can reduce, or the amount of energy that we observe as a rebound effect, denoted here as letter B. So this is an example. This methodology uses the available data, namely the response in energy consumption of the building and the penalty imposed that conducted to this response of the building. Here I can show you an example of a controller which is of a heating system that can be controlled to exploit the available energy flexibility. This flexibility comes from the thermal storage capability of this building. And I can show you here the difference between a conventional controller and a controller that exploits the available energy flexibility. So at the top plot, we have here as black dashed lines, we have the temperature limits inside the building. And we have two curves. The green one represents the temperature when the system is being controlled by the flexible controller, so the controller that exploits the available energy flexibility, and a red one, which is a conventional controller. This controller is focused on increasing energy efficiency, so it is maintaining the temperature as lower as possible. You can see that the temperature is most of the times close to the lower limit of this range of allowed temperatures. In the middle, we have the CO2 content of each unit of consumed energy, which is the solid black curve. And we have the status of each control, the conventional one and the flexible one, from 0 to 100%. And in the bottom, we have the cumulative CO2 consumption. So this CO2 consumption comes from electricity consumption, which by its turn has a specific CO2 content per unit of energy. As you can see, the flexible controller heating up the building when the CO2 content is lower. So when the CO2 is higher, it is not heating up the building or minimizes energy consumption during these higher CO2 emissions periods. While a conventional controller doesn't care about the CO2 equivalent emissions, it's just focused on minimizing energy consumption. So as a result, we have a flexible controller consuming 20% less energy over the period of 2 days. This is conducted over 2 days than the conventional controller. What is interesting is that the conventional controller is consuming less energy than the flexible controller. However, the flexible controller is consuming less or is responsible for less CO2 equivalent emissions. So energy efficiency is not the same as a reduction of CO2 equivalent emissions. Is of course a great. It's of course mandatory in many applications. Here we just have an interesting example where it is not the same. The other example I have to show, I have here to show you is refers to a study that we conducted to apply different methodology. We wanted to apply a methodology that uses information on the system being controlled, the system providing energy flexibility. And we studied the characterization and usage of energy flexibility provided by water pumping and storage systems. We collected data from a water distribution system in the center of Portugal. The typical vision for these systems is that they have a water source, they have a pumping station that collects water from these water sources, two treatment facilities that treat water and have large storage reservoirs for this clean water. Then from this clean water, we have pumping stations, pumping water to reservoirs close to the consumption centers. So this set of pumping station with final reservoir can provide flexibility as I will show you. So what we did was to characterize this flexibility and develop a methodology that allows this flexibility to be used both internally by the system operator to minimize electricity costs, for instance, or by external entities that can use this methodology to support operation of the distribution system of electricity, or the transmission system operator in case of the transmission system. So this, we started by collecting data from their SCADA system. Here we have the baseline operation. As you can see, this left plot represents the water level inside the reservoir from 0 to 5 meters. And you can see that the water is varying in terms of level throughout these 28 days. We choose from 28th of February to 27th of March because we choose this period because it's the period we have for the invoices collected. So that invoice will give us the amount of money we are saving by using energy flexibility, as I will show you. So for this operation, you can see that the water level is varying. That's because they have a rule-based controller on site implemented through the SCADA system, which is already very good. But we show that we can still reduce the cost by 16%. So for this operation, you can see here the load diagram of the pumping station during the same period. And here, for both the baseline and the scenario where we use energy flexibility, we have the water demand. So during the 28 days, we have this water demand, and also here on the right, we have the same profile, but per day. You can see as this blue curve as the average water profile. During night, demand is lower, of course, and then it increases throughout the day. So this flexibility characterization we proposed is based on energy cumulative consumption curves. The idea is that we have a maximum energy consumption possible during a specific period of time, and we have a minimum energy consumption possible during that same period. And here we are talking about cumulative energy consumption. So for this system, we could increase the energy consumed over a specific period of time by pumping water as much as possible until the reservoir is full, and when it is full, we would pump water as soon as the water level decreases from the limit. The same applies, the same analogy applies for the minimum value, where we restrict pumping until the water level reaches the minimum value, and we only pump water when this water level goes below the minimum limit. So almost infinite curves of flexible operation exist between these two. And this methodology, after characterizing by these energy consumption curves, can be used by both internal or external control systems. They just have to know these maximum and minimum curves and allowed power consumption values throughout the period of analysis. So if we have this characterization and we have the penalty signal, in this case, electricity price for business days, Saturday and Sundays, we just have to find the energy flexible consumption curve. And for instance, here we have this problem, and we solved this problem with a genetic algorithm, but other tools can be used, of course. So our job was to find the best flexible consumption curve after we have the characterization. Here we have some results of our study. We have the maximum and minimum energy consumption curves for a specific time period. In this case, for 24 hours. We implemented a model predictive control, so we would make our forecast for 24 hours in advance, and then we would apply the control for time step number 0. So for the next 24 hours at midnight of a specific day, I believe this is the first day of simulation, we have these cumulative energy consumption curves, and then we have the flexible consumption. As you can see, the flexible consumption is equal to the maximum limit during off-peak, which is the green period, and then goes until the minimum limit again since it is minimizing energy consumption during peak periods. Okay, and here we have the same curve for 6 hours later. They change, and also the flexible consumption change. As a result, we have this water level throughout the 28 days inside the reservoir. You can see that the full scale is used, but the limits are always respected, and these limits were communicated by the water distribution system operator. The load profile of the pumping station is also smoother than the original one, and the pumping cycles were reduced by 57%, hence increasing the lifetime of these pumping systems. In terms of costs, we totally avoid energy consumption during peak periods. We minimize during off-peak, and then, of course, it increases during super off-peak and normal off-peak. The amount of energy is the same, but it is consumed during different periods. And you can see here the average water level inside the reservoir, where it can be seen that the limits are always respected. So this is an example, another example where energy flexibility is used, in this case in a water pumping system, to reduce energy costs, while keeping the comfort needs. In this case, comfort needs can be translated to safety levels of the water level inside the reservoir. So before finishing my presentation, I present you here the ongoing projects where our group is working. We are working in 2 European projects, H2020, Positive and Janus. In both of those projects, we are deploying different technologies that characterize and use the available energy flexibility. And in Positive, in particular, we are leading the development of energy flexibility related technologies. Positive will deploy several positive energy blocks in Évora, and this fits well in this presentation because it's not only deploy photovoltaic systems to have positive energy blocks. This project is also concerned in accommodating this energy transition by using flexibility to avoid negative impacts and to increase the benefits of using these photovoltaic systems. We have also second life batteries here, the batteries that come from electrical vehicles, like it's a way of recycling these batteries. And for instance, we are controlling those batteries through algorithms deployed in our servers at Uninova. In Janus is similar, but approach here is to develop technologies on a VPP basis. And we also have the continuation of Annex 67, which is Annex 82. It started last year and will go to until 2014 year. The focus is energy flexible buildings towards resilient low carbon energy systems. And Uninova is involved in several tasks, namely mostly related with methodologies to characterize energy flexibility. And thank you for your attention. I'm now available for your questions. And before I forget, nice summer for everyone, and see you soon.
Thank you very much, Rui, for the great presentation and for also the motivation that for people that are like myself, who are not well into this area. It's great to see why research is being done in this area. Besides typical news that we all hear about renewable energies, electrification, and so on. I prepared a Padlet, an online platform for people that want to make questions. But if anyone wants to make a question right now, speaking the usual way, be free to do it in some time. If
Bruno? Only me?
No, I also lost Bruno. I don't know if the other ones.
Maybe a connection problem.
I also lost him, yeah. Mm-hmm.
Okay, no more questions for Rui.
No, we can go to this site. Should be there, the questions, right?
Yes, there are already 2 questions there.
Okay. What is your perspective on the user role, the behavior of building occupants in the overall success of these systems, and what can we do about it? This is a great question from Rui Neves Silva, which was my professor some years ago. Thank you. The change in behavior is also instrumental to achieve this energy transition. And 2020 show that it is possible to have these changes. Of course, those were mandatory and we didn't like it, but we can travel less by plane. We can have more remote meetings. And for instance, in these projects we had, probably the pace was not so strong as we would have if we travel and have face-to-face meetings where we can see each other in the eyes. But it shows that most of the meetings can be conducted remotely. Also, the other types of behaviors that has to be changed refer to even the comfort boundaries of our users, probably reducing set points in air conditioning. And many other examples exist where the behavior has to change to support this energy transition. Rui, I don't, you want to add something?
Yeah. Do you think that the installation of these energy efficient systems reduces the responsibility of the user in the overall process?
I believe the user should be engaged to be involved in these solutions at the first place. And the data from several studies shows that if the user is more aware of his behavior and the contribution, then it has a more efficient behavior towards energy usage, let's say. And that normally users installing this type of systems are more efficient. But this efficient is not always maintained for the entire lifetime. It decreases. So that's why it is the need to engage users is so important. Regarding the responsibility, I'm not sure if the responsibility will be reduced. It should not be reduced, and therefore everybody should be on board on this transition, and policymakers should do their job and motivate people to contribute to this. That's my opinion.
Thank you.
And also our job at academia to when possible, to show them that their behavior is also important to this transition.
Thank you very much.
Bruno has a question here. Thinking of electrical vehicles and its energy flexibility assets, having the peak solar energy production at noon indicates that the growth of recharging of these vehicles should be at noon. If this makes sense, shouldn't policymakers be promoting recharging infrastructures at workplaces? Yes, if we want to improve self-consumption by shifting EVs charging to noon, it is very important to have charging infrastructure at workplaces. And I believe in a certain way there are some incentives at the moment, like taxes. Companies that buy electrical vehicles have lower taxes, for instance, comparing to a diesel vehicle, of course. And this is an indirect motivation, let's say. And also peer-to-peer markets, or also other market mechanisms where users can charge the car during night, taking advantage of peak tariffs, and discharge during the morning when they arrive to their workplaces, to charge again during noon. So a vehicle to grid connection can be used to motivate the deployment of electrical vehicles, and at the same time supporting the energy transition by decreasing possible negative impacts of reverse power flows and higher peak demand at evening when people arrive home.
Okay, thank you. I have here another question from Ruben Costa, questioning your vision about the integration of energy flexibility with also electrical cars. To what point this model can actually be a reality, and how do you think the consumers and producers will pose themselves about residential energy-based solutions. Not sure if this is the right translation, but at least it's my best.
Okay. Users are indirectly motivated to use energy flexibility when the tariffs vary throughout the day. So if tariffs are more dynamic and if the electrical vehicles have in itself a controller of the charging process that it takes into consideration these tariffs, it can choose the best time slot to start the charging process. And but while this isn't still a reality, there are some demonstrations already, some projects taking place where the charging process is optimized in order to, for instance, improve self-consumption or reduce costs. In Positive, we are also leading a solution where we control the charging process of electrical vehicles at an office building in order to reduce electricity costs. They have a electricity price that varies in real time throughout the day. Well, part in real time, part is constant, and we are already implementing such technologies. On the market, there are already some solutions, but those are more rule-based solutions. Even the current electrical cars, you can select your charging schedule. So I believe users are well aware when they have an electrical car because it impacts a lot their costs. If you imagine that from peak to off-peak, you have a difference of more than 30 or 40%, you will want to charge your car during off-peak periods if that's possible. What's missing is technology to give more comfort, let's say, to the user. So here's my car, I will depart you at 7 a.m., please charge it and select the best time slot in order to decrease costs. This is the next step, and I believe we are close.
There are some more questions on the Padlet. One by Cancam about, I don't know if you want me to read it or maybe I can read it. So you mentioned smart building model that responds to the penalty and reduces energy consumption when prices are high. The first question is, what role does the user play in this decision? And the second, how did you ensure that the decision of the smart building satisfy the needs or preferences of the occupants?
Yeah, in this particular methodology, we assume that this controller that is shifting energy demand takes into consideration the user comfort needs. And that's the example in the next slide where we have these temperature limits that should not be avoided. It's the user who sets those temperature limits. Those have to be respected. This also tells us that if the user is restricting the use of energy flexibility by not providing a temperature range or something like that, then we would not have flexibility and we could not achieve the desired price reduction or CO2 emissions reduction. So the user is involved because it's the user who sets the comfort preferences, and those cannot be, those have to be respected all times, all time.
Okay. I have one more question, and there is another question that I think it's still being edited, but I think mine is very quick. So in example 2, you mentioned at some point that you use a model predictive controller, but at least it was not obvious. So is it the model predictive controller a basis to get the results then to put on the genetic algorithm to get your flexibility response? Or can you elaborate a little bit?
Yeah,
I'm a suspect because I'm a control guy, but at least
yes,
it would be good to hear about it.
Yeah, since we are using forecasting and we update this forecast at each time step, we introduce the data in our model, and we have again a different output. We then select a specific control strategy, and we have the horizon of the control strategies to be implemented, and we implement the one at time 0. So, for instance, in this, when we use the genetic algorithm for this optimization, we are varying the range of the different control strategies to select the best one. And we are doing this at each time step. And that's why it is model predictive.
So it's trying to get the best parameters for the controller to find the best results. Something like that?
Yes. Okay. The best control strategy in this case of the pumping system, it was at each time step if the pump should be pumping water or not, 0 or 1. It was a binary vector.
The other question on Padlet is by Danielle. Rui, thank you for your presentation. This thing we call energy flexibility can end up being called, well, I don't know if the authors want to say the question themselves, if they want.
Danielle is here.
Yeah.
Hi everyone. Thank you for your presentation. Yeah, I am familiar with the topic, but I did not get involved in the latest developments of the IEA annex. But anyway, I think it was just a reflection of mine, and I would like to hear your opinion about this. And then I have a question, of course. So when we talk about energy flexibility, we end up thinking on CO2 flexibility, user behavior flexibility, consumption flexibility, generation flexibility, depending on the case, depending on the state of the things in that reality we are dealing with. And I don't know if you agree with this. And then the question is, what kind of immediate strategy or thing to be implemented at the level of our campus as a good example of, demonstrator, as a good measure of energy flexibility to satisfy the CO2, because you talked about a lot about sustainability, actually, right? So I'm thinking about sustainability. Yeah, I know it's a tricky question. I know it's not an easy question, but yeah.
For the first one, and Daniel, you know my opinion, flexibility is not the end use; it's a tool. And this was my argument during the entire Annex 67. So we are not going to speak about CO2 flexibility or user flexibility. No, we are going to speak about energy flexibility. Now, for what is the purpose of using this energy flexibility? This energy flexibility can be used to reduce CO2 emissions or to improve self-consumption and so on. So it's a tool to achieve an ultimate goal. Regarding this second question, it's very difficult. We have to access possible flexibility sources in our campus. We have some, for instance, in our department, we have a chiller providing, consuming a lot of energy in order to, when it's on, in order to cool down our department. So if we could control this, the operation of the chiller according to the temperature inside the building, that would be a good source of flexibility, because I have analyzed those values in terms of energy demand, and it's the consumption of the chiller is around 70 kilowatt power, which compares to almost the same for the entire building, even less. So that's a huge source of flexibility. And now I I have problems with the president. Other sources are, for instance, the charging of electrical vehicles. We are starting to have chargers at our campus, and I believe if we analyze all departments, we will have and all buildings will have different sources of flexibility.
Okay, thank you. And we have our demonstrator, which is about to be implemented at Dulinova.
Yes, yes, and we are going to have a demonstrator at that. In terms of the campus, we will not have an impact, let's say, but it will be good to test some technology. Namely, we are going to have a battery and air conditioning in an office building, in an office of Unionova building. That will be interesting to collect some data to see the impact and if possible to test some control algorithms.
Yeah, I suppose there is no other question. So João Martins and Luís Camarino Matos have raised hands. João.
Okay, thank you. Okay, just one very, very short comment. Danielle is fully aware of this because he's an expert on facade. This usage of flexibility, namely the thermal one, as Rui was mentioned in buildings, well, you cannot have omelets without breaking some eggs. And if the building is from the scratch, poor thermal conditional building, then for much air conditioning and whatever you have, it's always a problem. Because in the case of the 10 building, so the building number 10 in the faculty, the thermal behavior of the building is very bad. So no matter flexibility you can have from this, it's always not as good as a building that starts from a good facade and a good construction. So I usually say to my students that there are smart buildings and intelligent buildings. Smart building is a building that you put some technology on it, some flexibility tools, and you try to manage energy efficiency. And the intelligent building, it starts from the architectural point of view, from the construction point of view, and you can add later on the technology, and everything went very, very well. So it's we must always think that it's not just a question of technology. You have also to have the ground to build upon. Okay, so that was just the comment I wanted to make, and congratulations, Rui, for the very good presentation.
Thank you.
So Luís, I think it's the next person.
Rui, thank you very much for the very clear presentation. I think you could make a very good overview of the area for all of us. So thank you. I have, and you also presented some of the works that you and the group in which you are involved are doing, which is great. So my question now is a bit trying to see how these fields can involve other knowledge areas from CTS. So imagine that you are not constrained to the group in which you are involved. Imagine that you have at your disposal, let's say, the whole CTS. So the task for you would be to assign activities or sub-problems to all the different areas of CTS. What could you do in that sense?
That's a difficult question, and I believe we have all the knowledge needed to exploit energy flexibility in this case, but for sure in other areas there is this knowledge from the sensor level at the building to the supervision systems that will control this flexibility. For instance, Bruno, our colleague, was referring that he is involved in model predictive control. For instance, this flexibility function is should be probably basic for our control colleagues. So for sure, they could help us in this field. Sensors, communication, supervision, decision making, all these we have in CTS, and we have some of the best in the world, and all of this is needed for our work. While it's still energy, but we have Daniel Aline working with us in this. He is from civil engineering, so it's even from the conceptual point of view, is even far away that our colleagues from telecommunications, for instance. So I believe this is an area, a field of expertise that needs the interaction between several groups, and I think we are achieving that, and it will be a pleasure to collaborate with some colleagues.
Since I've been named, I actually have the interest to understand better the problems and, if possible, help in any way about using MPC for using forecasts and optimizing responses given several constraints and defining different problems if possible. So I'm interested in those types of collaboration, but CanCam had raised its hand, so let's hear.
Hi, Rui. Thank you very much for your very insightful presentation. It was clear, and I liked it very much. My question perhaps may be out of context, but I'm hoping that you'll be able to throw some light on this for me. You're talking about energy flexibility. Renewable energy communities are also coming up as alternatives to energy sustainability. In your personal opinion, what role do you think energy communities could contribute to energy flexibility?
Mm-hmm. Thank you. Energy flexibility can contribute in several ways. First, they can be used to increase the integration of renewable energy resources. Then they can be used to engage users and to achieve overall sustainability. And also what we are studying, actually during my PhD work, I studied, at the time it was not called renewable energy communities, but we studied the collaboration of buildings at the community level. And what we could conclude is that when you conduct demand response methods at community level, you are also increasing or you are reducing the possibility of having negative impacts due to the increasing integration of renewable energy resources. So the communities, when you conduct, for instance, self-consumption improvement at the community level instead of building level, you have several advantages, namely reduction of peak load, less losses, and so on. So apart from the sustainability aspects of having more energy, renewable energy, user engaged, you also have this technical aspect of reducing possible negative impacts, because you are conducting the optimization of the available energy flexibility at an aggregated level, take into consideration what other buildings are consuming and generating in real time.
Thank you very much.
Welcome.
Any more questions? Okay, so I don't know if anyone wants to make any statement.
Well, I would like to thank you all for being here and for your attention, and I wish you a great summer to recharge your batteries. See you soon.
Thank you once again, Rui. Thank you everyone for the questions, and have a nice summer.